Yeah, hello and welcome from my side. My name is Simora. I'm the head of Adastra Munich. Adastra is an international data management consultancy, and we support our clients with everything data related. So from data acquisition, data storage, data architecture, cloudification, processing, pipelining, integration, you name it. We do the data governance around it. We do digital transformation and RPA and BI reporting and analytics. And the use case, which I've brought with me today, is about optimization. So how can you use your data to optimize your business? And in particular, it's going to be about the optimization of the parcel sizes, which is relevant for everyone who's sending their products either to end consumers or to other businesses. So let me directly jump in with a topic which is at everybody's minds right now. It's the COVID. COVID is one of the reasons why we are seeing a steep increase in parcels. So in the last years, even before COVID came into place, the amount of parcels which have been sent is on a steep increase. Plus, nowadays, or now it's Christmas time, so now everybody's shopping online and getting parcels sent to their homes. And if you get your parcel, it very often looks like this. So I'm very sure that this looks familiar to every single one of you. So you've received a parcel, you open it, and you find it to be rather empty. So a lot of void fill, a lot of filling material, and you wonder, why was such a big parcel used for shipping my product? A smaller parcel would have done the job. This is exactly what our client faced. So they get also a lot of complaints, and our client also ships their products both to end consumers as well as to other businesses. And in numbers, the average fill rate was at 53%. And 1 in 4 parcels was filled with less than 30%, which our client named shameful shipment, a term I'm going to use. So we came in from Adastra to improve the average fill rate. And when you think about this, the first thing you think of is the bin packing problem. At least when you're a mathematician, you think that. And yes, I admit I'm a mathematician. And the bin packing problem is very well researched, and but it's a very complex mathematical problem already. So it tackles the question how you should pack when you have a parcel. And what all of the variation which you can find in the literature have in common is that the parcel is given, or the parcels are given. And the question is, how should you split your items among the different parcels? How should you pack? But very seldomly, the other direction is approached. And this is what we did. So we thought, okay, what if we take the packing as given and optimize the dimension of the parcels? The big advantage of this approach is it's much more easy to implement. It doesn't disrupt any of your logistic processes. You simply go to your trusted parcel provider and ask for different sizes of parcels. And that's it. So you don't need to adjust or change anything. So we implemented a prototype. And well, as a starting point, of course, we use data. So what you see on the screen is some mock-up data, just to give you an impression of the kind of data we were using, and it's just a snapshot of it. There's more to it. Were more data, more complicated things, but for the sake of this presentation, I will keep it very simple. So on the left-hand side, you see order data. You see, for example, for this first delivery, you see a bunch of articles which were included and the given quantities of them. And on the right-hand side, you see for each article the dimensions, as the dimension obviously are very important to take into consideration when you are packing parcels, as well as the weight, same argument here. And you see a variable on the right-hand side called upright. which indicated whether this item needs to be shipped upright. So the default is that you can take any item and turn it around however you want, a little bit like Tetris. But for certain articles, you're not allowed to do that. So you can think of bottles, for example, which need to be stored upright. So we took the data, and as said, we also want to take the packing logic as given. So we had a look at the packing logic, which was implemented at our client. And again, I will simplify. And the packing logic, which was implemented, was actually relatively similar to the so-called first fit decreasing algorithm for the bin packing problem. So imagine you have an order. You have a bunch of items which need to be transported. And in the first step, you order them by size, with the biggest parcel being the biggest item, being the first. Then you take the biggest parcel you have at hand, you take the first item and you put it in there. Then you take the second item. You check, does it still fit in my first parcel? If yes, you put it in. If no, you take again the biggest parcel you have, the second one, and put the second item in there. Then you take the third item. Does it fit in the first? Yes or no? Does it fit in the second? Yes or no? And so on and so on. And at the end of it, you have split your order into parcels. So you've split the big order into groups of items, which together will be transported in one parcel. And as a third step, so additional, so to say, you optimize the parcel size. So you have a look if now you know the items which are supposed to be in the parcel. So now you see if a smaller parcel would also be sufficient. And if yes, you replace the big parcel with a smaller one. So this is a very frequently used algorithm and it's very simple. So that's the pro. But the obvious con is it uses large parcels with a high probability and also with a high probability of underfilling them. So what you could do, instead of the first fit decreasing, you implement the best fit decreasing algorithm, where you don't put the item in the first parcel where there's enough room for it, but you check all the parcels where there would be room for this item, and you take the one with the least free space, and you put it in there instead of the first one. But again, we were not there to change anything in the packing logic. We just implemented optimization on the parcel sizes. This is just for playing around at the end with the numbers. So we can have a look at the mathematical function in words. So from our optimization problem, the objective function is to minimize the unused volume of each parcel, such that, well, first of all the packing process constraints. Why is it important? Imagine we would split a large order differently into groups of items than the actual packing algorithm does. Then we would obviously suggest different parcel types and different parcel sizes to be optimal. This is why we need to map the actual packing algorithm and up to every single detail very specifically in our solution algorithm. Secondly, we have a bunch of other constraints. First, well, the obvious hard constraints, the parcel dimension and parcel weight restrictions, because, well, the parcel cannot be as big as it wants to be and as heavy as it wants to be. There are certain limitations to it. That is pretty straightforward. Then we have a bunch of soft constraints specific to the client, for example, compatibility with the pallet or the conveyor belt. And we've also introduced a penalty for the number of parcels. Because, for example, let's say you have a client who's ordered 10, 12 items from you. You can either put everything in one parcel and achieve a fill rate of, let's say, 60%. Or you can split those into 3 or 4 small parcels. You would increase the average fill rate to maybe 70%, but you then would also send 3 or 4 parcels to that end consumer, which you might not want to do. So you might just want to go with sending 1 parcel. And of course, we introduced a penalty for the average fill rate, as this is exactly what we need to maximize. Finally, we had a bunch of special constraints for our clients. Here, I'm just mentioning the fact that some goods need to be stored upright. There were more of them, but again, I'm keeping it simple. And yeah, now that we have our mathematical function and our mathematical problem, we need to solve it. And as there is no exact solution, we need to approximate the solution, and we decided to use a Metaheuristic algorithm, the so-called simulated annealing algorithm, and implemented that in our own optimization framework. So, a little excursus here on the exploitation versus exploration dilemma, which you in generally face when you do optimization. So let's focus on the left-hand side of the slide. This is your optimization solution space. So this is how all the values which your solution could, in theory, take. And you start somewhere. So you have an initial solution, and you evaluate your objective function. And let's say you end up here. And in the first step, you then start walking in some direction. And you either make things worse, then you stop and turn around, or you make things better. So obviously, if you're looking for a maximum, if you're looking for a minimum, you would try to walk down to this ground here. But let's take the maximization example. So you start here and you start to exploit your solution space, and you walk towards the optimum. And you evaluate your objective function over and over again, and you walk towards a local maximum. But if you just stay in this vicinity, you will at some point reach a local maximum, but that might just be local. So with a certain probability, you do not exploit, but you explore. So you jump somewhere else in the solution space, and you have a look at this in this vicinity. And you will find another local maximum, which might be better than your initial maximum or not, but you find another one. And after some time, you jump again in the solution space. You exploit that area, and then you jump again, and so on and so on. And at some point, you have covered at least most of the solution space, and you stop. So this is basically the simulated annealing algorithm. Here it's also once as a process chart. And the solution, the stopping criteria can, for example, be a certain number of iterations or a certain threshold that you want to achieve in your objective function. So this is what our solution algorithm did, and this is what it gave out. So what you have then at the end as an output from our algorithm is, for a certain delivery, which parcel should be used and what are the dimensions of this parcel. So let's take the second one here as an example. And for that particular order, we should use twice the parcel with ID 1, which has these dimensions, and once the parcel 3. What it also gives you directly is the average fill rate of these parcels there. And what you can see on the right-hand side is that we've been able to increase the average fill rate, and also that most parcels are now filled with between 70 and 80%, which was, by the way, our cutoff. And what's also important to mention here is, so we have here an example with 4 different parcel types. But this is a variable in our algorithm. So you can decide if you want to end up with 3 or 4 or 5 different puzzles at the end, and this will be taken into consideration. You can even say, I want to end up with, let's say, 5 parcels, and one of them should have a fixed dimensions because this is your favorite size, or you know that your customers frequently shop a particular product, and this parcel fits exactly to its size. So you can fix one parcel size and let the algorithm only calculate the optimal dimensions of the others. This is also possible. So in numbers, what did we get out of it? We were able to increase the average fill rate from 53 to 63%. And again, solely by optimizing the parcel dimensions. If we were to also implement optimization on the packing algorithm itself, we would have been able to increase that number to up to 70%. Then we've cut the number of shameful shipments in half. Completely getting rid of them is something just unrealistic, so you will always have the cases where you need to send parcels which are barely filled. And with that, you save approximately 10% of parcels and 30% of filling material, which translates to approximately 5,000 to 6,000 euros per 10,000 parcels. So if you now think, well, that's interesting, I want to do something similar. Our offer is that, yeah, we come to you, we do some workshops, we analyze your specific constraints and your packing process, and do the implementation and incorporate your feedback approximately over the course of 3 to 4 months. With that, you can, well, not only save costs, but also reduce waste, improve your environmental footprint, and improve customer satisfaction. Of course, the exact numbers very much depend on your status quo. So how is your logic now? How is your average fill rate now? And it will differ from our prototype. And lastly, we can also help with other optimization problems. So we now had the example of parcel size optimization, but we're also happy to help with with the optimization of other logistic processes or in general processes within your business. Just contact us, contact me directly under michael.simora@adastragroup.com. You can directly reach out to me. And with that, I've reached the end of my presentation. Thank you for listening. Thank you for your attendance, and have a nice day and stay safe. Goodbye.